Welcome, everyone. This is our fifth Computing Education Research Seminar of 2026, hosted by the Raspberry Pi Foundation. I'm Jane Waite, and I'll be chairing the session today. And in the seminar series this year, we're focusing on this idea of applied AI, where we're exploring research that examines how to best teach and learn about AI and data science across the curriculum. I can now introduce our speaker. I'm really excited and pleased to welcome today's speaker. So, Shuchi Grover, she is Dr. Shuchi Grover. She's here with us, and she's recently joined the Raspberry Pi Foundation as our Director of Research and Impact. So she's our boss. It's really exciting. And Shushi has got so much experience in terms of computer science education, particularly in the K-12 kind of landscape, and that's across both formal and informal settings. She's led all sorts of different initiatives, including the National Science Foundation funded projects involving the research and design of curricula, assessment, tools, and also the kind of the environments that help develop competencies in computing and in data science. AI and cybersecurity, as well as supporting integration across STEM disciplines. Um, Shuchi has also served on committees for the US National Academies of Sciences, Engineering and Mathematics. And this is where we kind of are today in terms of looking at their developing competencies for the future of data and computing, which is what's going to be looked at in the talk today. So that's what we're going to hear all about are the key ideas from the report, which identifies 7 shared competencies for data and computing and explores how these align with existing STEM standards and classroom practices. And Shushi's very kindly going to present examples of what that kind of integration might look like, focusing on overlaps with this applied AI theme of the seminar series and outline how K-12, CS and AI education communities can kind of draw upon and then build on this guidance. So really excited to have this presentation today. Thank you ever so much for presenting for us. So over to you.
All right. Thank you so very much, Jane, for that very kind introduction. Of course, I am thrilled to be presenting my third Raspberry Pi seminar and my first as part of the Raspberry Pi Foundation. Jane and the research team at RPF do such an amazing job organizing these wonderful seminars. So this talk, just to add to what Jane said in the introduction, it's all about a recent publication from the National Academies of Sciences, Engineering and Medicine, or NASEM, in the US that reports on a consensus study on foundational studies related competencies related to data and computing in school education. And I was very fortunate to be part of that committee that conducted the study. And for those who may not be familiar with NASEM, these reports are typically very influential in informing policy, research, and practice. Many of you may be familiar with How People Learn, the Bible of the Learning Sciences, that emerged from a consensus study. The hugely influential National Science Framework in 2012, which led to the Next Generation Science Standards, and several other reports over the years. So often these reports are the starting point of a lot of downstream activity taken up by funding bodies, curriculum designers, researchers, policymakers, educators. And it's our hope that this report also, that is the case with this one as well. And like other National Academies reports, this one is primarily US focused, but I believe the findings have global relevance. So this report is not directly about applied AI, which is the theme for this seminar series, but these competencies are very pertinent to AI education in K-12 and especially AI in the disciplines. So I'll give a quick overview of the report, devote some time to discussing the touch points with AI, and then we'll have all the breakouts and all the fun stuff. So I've always believed that why is a great place to start. Why this report? As you're all aware, about 10 to 15 years ago, computer science education saw a major resurgence, and it was framed as an imperative for all. CS for all became the hashtag. Computational thinking, funding for research, development, capacity building, teacher preparation, all of that followed, and this was a global movement. And then data science started to emerge. Although it had existed in some form in maths and statistics for a long time, began to receive increasing attention prompted by the big data revolution, etc. And so there was a call for standalone courses, funding, learning progressions. And now AI is running the same playbook. There's funding is moving there, for all organizations are popping up, standards are being written, and we're already hearing calls for quantum computing. So you see where this is going, right? Schools and teachers are constantly getting bombarded with increasing frequency to teach each new shining thing that comes out related to advances in computing. And so today we have a CS course in some schools, but not in others, a statistic module bolted onto the end of a math course somewhere, an AI elective pilot here, a data science partnership there. None of these efforts relate to each other. And this reality often conjured for a vision of a messy garden for the community, where you can see things growing, but you cannot see a cohesive picture. And this is a quote from Nick Horton, the committee chair, that captures this sentiment well. So the challenge that we wanted to address was, just bringing coherence to these many disparate efforts, dealing with the problem of a crowded curriculum, and of course, the growing urgency as technology is reshaping work and society today, especially with AI. And so, like every other NASEM consensus study, this one was handed a statement of task that we were charged with addressing. It's long and wordy. I don't expect you to read it, but this is what it essentially boils down to. What competencies and awareness are needed for learners to develop basic literacy in data and computing? How are the foundational competencies for these fields related to foundational competencies in other STEM fields? What should be relevant learning experiences? What should they look like in practice? And how might these experiences be tailored to meet students' interests and lived experiences? And what are the implications for curricula and the broader K-12 education ecosystem? The study was sponsored by the National Science Foundation. A 16-member interdisciplinary committee, supported very well by the staff from 3 NASEM boards, was convened. The committee met multiple times over 2024-2025. There were 3 public fact-finding meetings over that time, including state-level landscape from various representatives in the community, from DS4E, ESEP, etc. Professional organizations and classroom implementation examples were presented. And then there was meetings around assessment and connections to career and technical education. There was finally an external review of the report leading up to the report release in March 2026. So this is the study committee on whose behalf, really, I am presenting this work today. It was chaired by Nick Horton. And as you can see, it included researchers from various disciplines: science education, math education, CS education, data science, statistics education, in addition to members representing state policymakers and curriculum designers. If it's mostly a CS education audience, you might see familiar names from our community: Aman Yadav, Victor Lee, Janice, Sapir Vakil, Shani Daly, and myself, of course. So this is the report by the numbers, as they say. It's pretty long, 340 pages, which is why webinars like this might help you sort of navigate it. It has 9 chapters that take you where we are, what students need, to how to get there. It has 21 conclusions, 14 recommendations, 32 research questions. And this is the way the report flows. Chapter 3 is where the foundational competencies occur. 4 is where connections are made to other STEM standards, etc. How to design effective learning experiences and curriculum, preparing and supporting teachers, how to deal with systemic change. And of course, the report ends, like every other consensus study, with recommendations and a research agenda. So the starting point for us was where we are today, and the study began with an in-depth look at the current landscape. And this involved reviewing existing standards and frameworks and actively considering what's going on within computer science and data science and mathematics and statistics and science. And it also extended to looking at AI and quantum computing related research. And in fact, one of our fervent hopes is that these standards are revisited and tweaked to forge that coherent vision that this report lays out. And so, based on this sort of bottom-up combined with top-down deliberations, we arrived at several candidate competencies, which were finally boiled down to a set of 7. And here they are. Drum roll, please. So, problem posing and problem solving, producing and working with data, abstraction, algorithmic thinking and automation, probabilistic and inferential reasoning, models and representations, technology and society, data and computing systems. So someone said to me soon after the first webinar in March that, well, these seem kind of obvious. Where's the groundbreaking new framework? Or if you're a teacher, you may be thinking, well, I recognize all of these. I do some of these in my classroom even today. But that is precisely the point. These were not meant to be exotic or new. They're meant to be recognizable. But just because these are familiar doesn't mean that they're being taught with intentionality today. The ideas have been floating around in our classrooms, but most times they are implicit, incidental, and often invisible to students. And what this report does is it names them, elevates them, connects them across disciplines, gives us all a shared vocabulary to talk about them. And I should say before proceeding that these are not in any priority or order. I mean, we just had to lay them out in a certain sequence, and this is what it is. So it's not as if it starts with problem solving and ends with number 7 or anything like that. So I'll go over each of these now because it's important to understand what these are. Competency 1 is problem posing and problem solving processes. How students approach problems in STEM disciplines. And we identified 3 core components: defining a problem or question, identifying the steps needed, including things like decomposition and pattern recognition and those kinds of things that sometimes happen in some instances, and reflection and iteration. And understanding that the process is cyclical and not linear. And so a key insight for learners is that in the real world, problems don't come predefined, and answers are seldom achieved in a single step. Work proceeds in tentative steps with frequent pauses to reflect and course correct. And this basically mirrors process cycles that you see in various STEM disciplines and contexts. And though there are disciplinary differences here and there, all of them share the same core structure of define, attempt, reflect, iterate. And importantly, the reflection step includes considering how data and computing solutions can have societal consequences. Conclusions drawn from incomplete data could be misleading, and algorithms trained on biased data can be harmful. Competency 2 is about producing and working with data. In a world increasingly full of data and dependent on computing, students must understand what it means to measure, how data can be produced, and how it can be organized and visualized. And the report makes a crucial distinction about data being produced rather than just collected. All our actions, for example, in the digital world are producing data that someone is capturing and using. And every measurement involves consequential decisions. So the second component is about data organization, which the report calls data moves, filtering, aggregation, creating new variables, merging data sets, all those transformations that are needed and are essential before any kind of meaningful analysis can happen. And the third is exploration and visualization. And students can start visualizing data right from kindergarten with things like tally charts and progress on through complex multivariate displays in high school. Data provenance matters deeply. When using someone else's data, students need to ask who collected it, from whom, when, where, and for what purpose, and who might have been left out. Competency 3 is the one that, of course, is connected, deeply interconnected, competencies of abstraction, algorithmic thinking, and automation, which come from computing. And you'll see sort of computational thinking in this one. Abstraction, of course, is representing something in simplified form and capturing essential features while ignoring extraneous details. Computer science is sometimes called the science of abstraction. In data science, for example, abstraction shows up when creating histograms rather than presenting raw data sets. Algorithmic thinking, as you know, is about creating ordered sequences of unambiguous steps to solve a problem, and not just existing algorithms, but designing new ones, including breaking complex tasks into subtasks and anticipating conditions for different execution paths. Automation becomes necessary when scale grows, and that's something that students need to understand more and more than we have in the past. And students should not only understand what automation brings to the table, but also learn to decide when a solution will benefit from being designed for a machine to execute, and how or when a data set or model becomes so large that it absolutely requires computer automation. And then to also think through both the benefits and the drawbacks, etc. Competency 4 is an interesting one. It's a skill that humans use daily, probabilistic and inferential reasoning, and often without realizing it. But it's also one that is sort of not, it's sort of the least well taught currently. And I think this is the one that benefits most from AI literacy efforts. It's especially critical now to understand machine learning and generative AI, because these are systems based that produce output based on probability. So again, three components. First, identifying sources of uncertainty and variability from measurement, sampling, and natural variation. Second, recognizing the different roles of probabilistic, statistical, and deterministic reasoning. And in fact, the report shares two very vivid examples. One of weather forecasting, where predictions are probabilistic, and the GPS, which is clock accuracy affecting location certainty. And in both, deterministic equations underlie the systems, and yet the outcomes cannot be known with perfect certainty. So these are the kinds of understanding students should develop. And the third is about making inferences and predictions with appropriate degrees of certainty. It's a skill that students can begin developing pretty early on with informal inference, and then progressing to formal hypothesis testing, etc., in high school. Models and representations, of course, appear in every STEM domain, albeit in slightly different ways. They are tools for organizing information, communicating relationships, and predicting outcomes. They're objects that stand in for and correspond to something else in the real world. They range from simple graphs to complex computer simulations. They reflect important features of an object of study for explanation and prediction. And importantly, they depend on underlying assumptions and choices, and they evolve with updated input. And the report highlights a critical tension in the age of AI. Even as technologies are becoming more and more advanced and sophisticated, limitations remain. A digital twin is still a simulation. It's not the true thing. An AI-generated image of people cannot be a reliable evidence of actual behavior. Three components again: constructing and using models, assessing their quality, and recognizing their limitations. And a very powerful example in the report is from the 2025 LA fires. Layered maps show the locations, wind direction, and at-risk neighborhoods. And these illustrate both the predictive power as well as the very practical stakes of models and representations. Competency 6 is an increasingly important one today. It frames the relationship between technology and society through social technical systems. So it's a combination of social elements, humans, roles, power structures, and technical elements, tools, infrastructure, and how they interact and influence each other. Its components include reasoning about process and product. New technologies don't just change how a task is accomplished, but often redefine what is being created. And this tension is especially relevant in Gen AI, where it's so powerful that it solves complex problems, but still, makes mistake on very simple things. Second, reasoning is about reasoning about self and society. And a critical insight is that focusing exclusively on individual choice can obscure larger structural dimensions of technology. Individual users may lack the visibility, power, or information to address systemic issues through personal choices alone. Values like security, autonomy, fairness, privacy, and inclusion can be simultaneously present and in tension. Biased data sets can lead to harmful outcomes in hiring, policing, lending, etc. And so students need to learn about direct consequences, but also secondary consequences that emerge as systems scale, and then tertiary consequences that, may take decades to surface and become apparent. The last one is data and computing systems. It addresses students' knowledge of the use and knowledge and use of actual tools and infrastructure that make everything else possible. Systems that are omnipresent for us today and often, they change very frequently. And most students today enter kindergarten having already interacted with many computing systems. And yet, interestingly, without formal instruction, many will graduate thinking that these systems are engineering magic or too hard or not for them. And so, they need to learn about these things and sort of to demystify these systems. And so the components include recognizing elements of data and computing, hardware, software, how information is encoded, processed, etc. Selecting and using appropriate tools for a given purpose. I mean, no tool is best for all tasks. And of course, understanding things like ownership, openness and access, data privacy, consent, open source, environmental impact, all those things. And the report does highlight generative AI and quantum computing as examples of how systems are continuing to evolve and why this competency of adaptability matters for the future. All right. So one of the report's key methodological moves was to analyze existing frameworks in the light of these 7 competencies. So we looked at the computer science standards, the maths and science standards, the GAZE standards from a framework from statistics, AI for K-12 big ideas. And this is just an example of how, we found those competencies already sitting in frameworks, and sort of the chapter itself has, much more detailed tables, etc. And the report talks about elevating the competencies, since to a large extent, they already exist in existing math, science, CS, engineering standards. So a science teacher, for example, doing data analysis is developing competency 2. A math teacher teaching algebraic variables is doing abstraction, is teaching abstraction, competency 3. And when a student creates a scatter plot in math, they should know that it's the same competency that a data scientist uses every day. And so, but these connections are rarely made explicit currently to students. And so, the time that's spent on them, and especially in primary grades, is currently insufficient. And so the goal is to sort of elevate what's already there, but make it much more apparent, much more intentional, give it more time. And chapter 4 does all this mapping and finds all the touch points. So just to give a very quick example, it sort of finds what the areas, productive areas for connections are. In maths, for example, measurement, algebraic thinking, probability, and modeling can be enhanced with explicit connections to data and computing. In science, there are concepts like scale, proportion, models, asking questions. All of these connect to data and computing very well. So the report then spends 2 chapters on discussing how to design. After doing the what, describing the competencies, we move to the how and designing these learning experiences. And it starts with sharing what effective learning looks like and what it means. That learning is active, social, constructive. It builds on prior knowledge and lived experience. We discuss pedagogical considerations, problem and project-based learning, real-world context, and ethics throughout, co-design. There are examples by grade band in this chapter. And there's a good discussion on tools for doing this. And again, there's no perfect tool. One has to choose a tool based on the learning goals. There are tools for data and computing like CodeApp, NetsBlocks, which extends, Snap to bring in data sets, the Scratch, Jupyter Notebooks. And importantly, the report gives a lot of importance to unplugged learning and how that is very valuable. So just because a school may not have access to devices, etc., does not mean that they cannot learn these competencies. And that's a message. That's an important one. A few key conclusions from this chapter are that learning experiences must connect to students' lives. Learning must begin in primary school or elementary school. And interestingly, there are opportunities for leveraging generative AI. Given that it's already in classrooms, how might we leverage it for, talking about some of these competencies, but also, talking about use of AI, evaluating validity of AI outputs, etc. The big message from this report around design of curriculum is that integration is a very realistic path through the current school structures, especially in K-8. And the report does not really preclude standalone courses, especially at the high school level or middle and high school. But for the earlier grades, it feels like integration seems to be the most coherent and preferred approach. This chapter talks about various approaches to integration, which is a good rubric to have sort of. Anytime you're doing integration, it may not always be interdisciplinary or full integration. You could still be doing something that's, at a partial level, but knowing what level you're integrating at is important so that you can aspire to some of the more, full disciplinary, interdisciplinary integrations and such. There's lots of examples by grade band here as well. And so what I'm going to do is now look at 6 examples by grade band. And these all come from these couple of chapters. So the first one is a primary school example. It comes from Shamway and colleagues. Kindergartners engage in unplugged algorithmic thinking, such as sequencing the events of books like We're Going on a Bear Hunt, or programming each other to move around the classroom, and games like Robot Turtles. And then that's followed by programming 2 different robot toys to navigate a grid in small groups. The researchers found that the children grappled with mathematics that goes well beyond the where typical kindergartners are at. They counted movements rather than discrete objects, coordinated one-to-one correspondence between physical moves and code blocks. And I would love for you all to look at this work just for the theoretical framing as well that they do. And so it's a great example for all that the kids accomplish in mathematics, but through unplugged and coding activities. Another example from elementary grades comes from my friend Marcelo Worsley's PE++ work. It's a research practice partnership between Northwestern and Evanston elementary schools, where university researchers worked with both coding and PE teachers to co-design activities that span both classes, and students program microbit variables to track steps, laps, mile times during PE. They build scratch projects to connect to physical movement, and students experience both CS and PE as connected rather than separate subjects. And since most, integration efforts are in STEM subjects mostly, or maybe social sciences, I think any example that comes from outside, I think is very interesting. And yes, students develop concrete examples for otherwise abstract data and CS ideas. So variables and the quantified self, etc., is a great way for students to engage in both data and computing. The Shrinking Lands project is the report's, featured culturally relevant and responsive example. It draws from Hansen and Christian Searle's work. It's a project that's part of a larger middle school social studies unit focused on treaties and sovereignty. Indian treaties in the US, students construct and program a map using computational circuits that overlays tribal land areas before and after a series of US treaties, letting students visualize the loss of tribal lands over time. And social studies, as you're all aware, is often seen as a fabulous context for meaningful integration of data and computing. And this is an excellent example of how to develop those competencies of problem posing and working with data and algorithmic thinking and creating models and representation, but also looking at the socio-technical aspects, right? The socio-political aspects. And the framing in this paper is around culturally relevant making. Again, a lovely paper to read. Another one is adapting the data science for social good curriculum that's used a lot at the undergraduate level here in the US, and adapting that for middle school and having students, work with both blocks and text. And so bringing in some computing education, learning goals, but also looking at problem posing and how to sort of connect to real world activities. This one is from high school. It comes from my own work with the CS Frontiers team, where we used Nets blocks, an extension of the SNAP block-based programming environment created at Vanderbilt that opens access to public data sources and services. So in this intervention, Students worked with 150 years of data from NOAA, which is the National Oceanic Atmospheric Agency, and data from ice cores, carbon dioxide measurements, and global temperature, etc. And it was basically a very authentic interdisciplinary context for climate science inquiry. Students posed their own research questions about long-term climate patterns. They wrangle data, pre-process the data, build visualizations, and then interpret the visualizations to answer the research question. And the report, of course, names 4 competencies. Within C3 itself, it actually looks at algorithms and automation and abstraction in some sense, all the 3 things that are in competency 3, but also problem posing, data wrangling, statistical and mathematical modeling, etc. And one way in which this was really interesting is that the goal was to engage girls, especially in advanced data and computing, and in the context of climate research. And so it was led by a team that included a woman paleoclimatologist and a woman science education researcher. And so, there were equity considerations built right into the pedagogical designs of this unit. The last example is from an AI literacy effort at the high school level, Story Q on CODAP. From Jiang and colleagues, students train a sentiment classification model on a corpus of online restaurant reviews. They iteratively select features, examine a confusion matrix that compares model predictions against human labels, and they try to improve test set accuracy. It's a great project since, in my view, it actually hits all 7 competencies, I think. Investigation cycle, algorithmic structure, probabilistic reasoning, modeling and representation, ethics, and, whose voices are in the corpus, and of course, systems question of what's actually happening under the hood of NLP tools. It's also a great example of how a well-designed AI literacy and applied AI unit can look like. So that's a good segue to actually now discuss a little bit about AI in this report, given that that's the theme of these research seminars. One obvious question that people have asked is why this report is not more explicitly about AI. And our stance, which of course comes from the statement of task, is that data and computing competencies are foundational. If students understand these competencies, they will understand AI. In fact, they can and will learn many of the competencies through AI education itself and AI literacy efforts. And so the report talks about ML as a kind of modeling technique that relies on compute and data. And the current AI revolution is machine learning. It basically rests on a foundation of data and computing. And there can be no AI ML literacy without data literacy and computational literacy. Second, the report scopes the work mainly around teaching about AI. Wherever it's talked about AI, it's not so much in the context of use of Gen AI in the classroom, but it is about teaching AI. And so it's the with AI question is treated as part of an open research question on how Gen AI could potentially help in building these competencies. And also, it basically cautions explicitly against, thinking about AI only as Gen AI and about LLMs. Students will encounter many other different kinds of AI, especially in the future, and the framework needs to be able to absorb new forms rather than be built around this current instance of AI. The report has several AI-based examples. In addition to the StoryQ project, there's one around decision trees from decision cards. It has AI methods in data science. It has a Do You Trust AI tool and TinyML in K-12 for lower resource schools. So several good. The report is really very rich in several examples of all kinds. And so I would really urge you to take a look for whatever topic you want to see, whether it's for the competencies or whether it's for grade level or whether it's in a specific subject or it's around AI. There are other AI-based examples like a pet image classifier for competency 4, probabilistic reasoning, and for competency 4 and 5, next token generation in a generative AI model, facial recognition and algorithmic bias is discussed in the one around technology and society as our filter bubbles in recommendation systems. Environmental cost, bias, all of these are discussed in a lot of detail. So AI features heavily in the report, even though it's not there in the title. AI features in the research agenda itself. There are 3 questions around how will the use of generative AI be an aid for coding impact, generative AI as an aid for coding impact the need for K-12 coding instruction. This is something that the CS education community is, of course, facing and looking at. And of what are the anticipated shifts in teacher training, student content knowledge, and curricula? How can future instruction emphasize new developments related to data and computing, such as AI and quantum information, etc.? And how does the use of AI impact students in instruction? And one of the comments in the report is that, the increasing use of Gen AI, how can we leverage the excitement and hype around AI to teach these foundational competencies for data and computing? I've often in my previous talk sometimes talked about, the Trojan horse. Given that people want AI in the classrooms now, we should use that to bring in these foundational competencies of data and computing because they're so connected to AI examples as well. Before ending, I want to very briefly cover a few final sections of the report. Chapters 7 and 8 talk about teacher preparation and transforming the system, all the very easy stuff. Teacher preparation, I mean, these are things that everybody around the world, these are globally applicable. Instructional guidance is lacking, especially for primary grades around this kind of work. In service, a lot is done around in service, but it isn't, uniformly available. And pre-service teacher preparation programs really need to sort of shore up to include these things. And so that needs to be addressed. And, the system change, of course, involves multiple levers and levels and actors from policy and, of course, coordination at the national and state level and local levels. Interestingly, the report talks about families and communities, and I really hope that there is a lot of traction that it gets around this piece. I think it's very significant that it calls out for engaging families and of course, not looking just at in-school time, but out-of-school time as well. The report ends with recommendations and a research agenda. The recommendations fall under 3 buckets: adding data and computing to K-12, many of which sort of flow from whatever I've already talked about, supporting teachers and transforming the system. The research agenda is 32 questions around 5 areas: curriculum design, implementation, professional learning, the most number of questions there, system supports, and measuring impact. And a few select items, I think, from the research agenda, just to give you a sense, but you can imagine how many different things we could be researching around this. And so the research questions in the report are just meant to be illustrated, and they're not exhaustive. But they are very much along the lines of what we all want to understand. What pedagogies best support student learning about data and computing? Is it consistent across the foundational competencies? And how will the use of Gen AI, this I've already talked about. How does the use of AI impact? This I've already talked about. Again, bringing in more AI questions here because this seminar is around that. But what are common roadblocks and misconceptions related? And are there common pedagogical practices and approaches across STEM disciplines, or do we need new ones? And this last one is also interesting. What is the impact on young people's perceptions of various disciplines, and what participation changes are seen when the foundational competencies are integrated? And that's an interesting question. So I'll end with the key takeaways of the report, that there is a real risk of overload unless we find some cohesive, coherent way of integrating all of this into K-12 computing. You can't keep adding a new course and making room. It's just not going to happen. Common ground already exists. And so there are shared competencies that undergird all these fields. And to a meaningful degree, they're already there. And so there are 3 paths: make existing data and computing connections more explicit, enhance connections in science and math, and expand the role of data and computing in K-12 learning experiences, starting in kindergarten.
Thank you ever so much. That was a wonderful presentation. Let's give Shuchi a wonderful round of applause. Thank you so much. Talking about media literacy, because now I've actually got to I get a chance to talk about our next seminar. Please do come back. and we're going to have Gianfranco Polizzi, who's from the University of Birmingham. He's been presenting at various select committees and is very much involved in the redesign of, or what's going to happen in terms of the redesign of new curriculum, particularly around media literacy. So exactly what we were talking about before. So please do come along there and thank you. You can put your mics on now and say goodbye.
Everyone.